Okay, I'll get started. So the presentation maybe will be somewhat different to the presentations from today and probably quite different from yesterday as well. So a lot less statistics focused, thankfully, and more kind of focus on computer vision and maybe some more real world applications, which kind of borrowing ideas from computer vision and integrating them into computational imaging. So it'll be relatively interesting, and I'll try to speed up as well. The idea is extending the equivariant imaging ideas from the past few years to new problems, and then these new problems might come with different properties to do with the imaging or the imaging system, and then can we leverage that to improve the results? Yeah, so okay, because most of this has been introduced already, so I'll go quite quickly through the introduction of what are the imaging things we're considering, why we want to use unsupervised learning and equivariant imaging is obviously already being introduced. Um, and then the kind of main topic will be kind of taking groups from so kind of mathematical groups inspired from things that exist in the real world and see if we can apply that to improve the results of equivariant imaging. And then just some results recently from the past year, and then just it'd be nice to have some food for thought, especially from you guys with some kind of more mathematical background than me, probably. So the inverse problem we're considering again, so kind of the ill-posed problem where A is not full rank, and then we're considering some noise on the measurements. So kind of the same equation that's been considered already for the past day. So in this particular example, it's of dynamic MRI of the heart. So we're imaging a certain cross-section of the heart. And it's a video, so it's 12 frames, and the measurements are very, very sparse. It's 8 times acceleration in the Fourier space, and then the mask is varying as well, with some noise added. So the goal is to learn a solver f parameterized by theta to solve this inverse problem. So some other examples of this inverse problem in the real world. The heart you can consider as a relatively easy problem because it's beating, you could assume, with some kind of periodicity, which makes the problem easier. But then we also want MRI. We want to take MRI of real dynamic things in the body. So, for example, breathing, which might be irregular, much more irregular, or speaking, or bones moving, for example. So
Is this multi-coil?
this is a single coil case, but I mean, generalized these to a multi-coil case. So in these next couple of inverse problems, maybe you can think about, is there ground truth for this kind of inverse problem? The next problem that we'll consider as an example is satellite imaging. So in satellites, you want to image a scene of the Earth, and you're imaging that with a satellite which has two cameras on it. One is a much lower dimensional, so downsample, for example, 4 times or 8 times downsampled image on the left, which is the YMS, so the multispectral image. And then you also have another camera which has the higher resolution but no color image. So you can see there is also a null space in this problem that you're losing spatial dimension and also the colors of the image, and you try to recover that. So again, in this case, you can think about, is there a ground truth for these two examples? So in the dynamic MRI setting, the heart or the breathing or the speaking is moving at much higher rates than the MRI machine, where you can lie there for hours and hours. So for example, with a knee MRI, you can lie still enough to take a static MRI, but the heart, it's physically impossible to take real-time samples of motion. So you have to put lots of assumptions in practice. So the current kind of standard way of imaging the heart is you assume the heart is regular, and then you let the heart beat for many, many, many iterations, and then you kind of retrospectively fill in the samples. So you have to assume the heart is kind of what we call gated by, for example, EEG. You have to assume the heart is beating regularly, which kind of defeats the whole point of heart imaging, where you want to be able to image kind of arrhythmic heart or kind of arrhythmias in breathing as well. So ground truth does not exist in scenario. So for satellite imaging as well, this image does not exist in the real world, because there's no satellite that can take this. The satellite only sees these two measurements. Yeah. So okay, breezing through this. So supervised learning, yes, you have to have the ground truth. So if the ground truth is created from some fake means, so this is not a real ground truth, it's a ground truth just created with a classical method where you just try to fill in the colors with the downsampled image. If you're only ever comparing to ground truth, which is not real ground truth, then you're never going to be able to learn anything that's actually in the real scene, which is not in your fake ground truth. So, for example, with your dynamic MRI of heart, you'll never be able to learn the areas of the heart. So we want to be able to do some kind of unsupervised learning. So this is the naive measurement consistency. And then, as Mike and Huli mentioned, if the A is an ill-posed operator, then we can fill in any gap in the null space of A with any vector we want in the null space, and that will still be measurement consistent. So for the satellite imaging, you could imagine like there's a small swimming pool, that's an example that Huli was working on, and then you can't observe that in the swimming pool is blue, for example. There's quite a lot of red swimming pool. You won't be able to observe in the black and white, and it will be too small to observe in the downsampled, so we won't be able to observe our fake ground truth. So we won't be able to recover it with any of these.
Why do you want to detect swimming pool?
If I tell you, I'll have to think. Okay, so with equivariant imaging, it's we're using a simple natural, that's kind of important. It's a natural assumption, or maybe some kind of blind belief, alluding to some of the questions yesterday. That you have some kind of belief about this unknown set X, which you do not observe, that it's invariant to a group. So, for example, in the literature considered so far, so we have our transformation is a linear representation of the group. So the 2D images we are to. And what we want to consider is, can we go beyond these linear or discrete or locally compact groups that we considered so kind of simple groups, so discrete groups like the pixel shifts, or the locally compact groups like 2D rotation, and which all kind of have linear actions. Can we consider bigger continuous groups, non-locally compact groups, non-linear actions where you can't describe the action as a linear representation, or even non-geometric groups, so groups going beyond the spatial dimensions. So yeah, maybe you can think about this, and if you have some kind of background knowledge of different kind of groups. So I just want to show some examples that we're thinking about. So in the MRI case, so this the original equivariant imaging paper, we're looking at 2D rotation, so that's a knee, and then we also rotate it in 2D, and then we also believe that's a knee, and that's kind of quite plausible because you could enter the MRI machine at like some degree of rotation in the MRI machine. Sticking it that way. And then, okay, so then we think about, for example, a 3D scene image with an optical camera. This is the chapel in Christ College in Cambridge. And then let's say you're standing in this chapel, which I've done many times, and you turn around. Are these two images related to each other? And these transformations, are they actions of some group? And then we show that, yes, this is actually actions of a group that's isomorphic to 3D rotation. So we're going way beyond the 3D rotations to a group in 3D. So here's an example of this is not kind of a blind, unnatural belief anymore. You're thinking about how can you construct this group based on how this imaging system works in the real world. I'll dive a bit into the camera geometry because I think it's quite interesting. Just a second example, another belief that we could have, so rather than looking at imaging systems, we're looking at the imaging subject. So in MRI, for example, you can have some kind of belief that not only the knees or the hearts you can rotate, but you can also squish them. Or maybe like if you're imaging a brain, people's brains can be squished and they still look like a brain. I'm not a medical person, but you could have that belief. And so, for example, you can think about the diffeomorphisms, so kind of diffeomorphic warping maps between, for example, on the left and on the right piece. You can still use this assumption that this is still part of the same set. And then this group is way non-locally compact and includes everything that we've considered already. Another example is a non-geometric group. Now, because now our data is not just in the spatial domain, we're looking at the video domain, so we can consider a group as well in the temporal dimension. So we shift the video forwards in time, and we recover the dihedral group in time. So a backwards video of a heart beating is also a video of a heart beating, for example, or a heart beating shifted by 1 second is also a video of a heart beating. So can we also use all of these further groups to constrain the problem further and get better results? Just as an aside, so focusing on this example, I thought it'd be quite interesting to dive a bit deeper into this. So how can you construct this group? How do we arrive at this conclusion? And it's quite a nice link between what we've been studying in inverse problems and this classical computer vision. So this stuff from decades ago on classical projective geometry. And then there's this result that you assume that you're imaging with a camera and you're imaging a scene. And if you, maybe I'll drop the board. So there's two scenarios here. And if you, so for example, your camera, and then your imaging scene here, and this is your field of view. If you stay in the exact same location and then just rotate your camera to this field of view, then the image imaged by this camera and the image imaged by this camera facing this way, you can describe the mapping between these two exactly with a matrix transformation. And then this transformation is actually part of this projective general linear group in 3D, so adding an extra dimension. It's linear in 3D, but non-linear in 2D. So the other interesting corollary of this is not the only scenario where you can map the two images with a matrix transformation. The other setting, which is much more pertinent to satellite imaging, is you assume that the world is flat. And then you have two satellites imaging the world at arbitrary rotations and arbitrary translations between each other, arbitrary scales. So this satellite could be here, it could be not that arbitrary, maybe this way. Any image imaged by these satellites can also be mapped from one to each other by this transformation matrix, which is quite cool, I thought. And all of these transformations are actions of this group, so it's a very, very general group. And then you can actually go beyond this and they're not just kind of arbitrary transformations, you can parameterize this transformation. So again, if you assume we have pinhole cameras, which is often the case in the real world, maybe less so with satellites, but you have cameras, for example, with the camera in your phone. And the transformation can actually be parameterized by real physical parameters. So the theta, x, y, and z is your rotation of the camera. So according to these parameters here, the theta z will be a rotation in the z-axis turning head, and theta x and y will be turning curve. It's kind of panning and tilting rather than this the other one, roll transformation. And these kind of your parameters of your camera, so your principal point of the camera, the skew of your camera pixels, and your focal length of the camera. So these are real parameters that are in real cameras. And then actually by fixing these parameters in this transformation, we can recover subgroups of the projective general linear group. So for example, if we're fixing theta x and theta y, we can't pan and tilt, we recover affine group, which is a subgroup. And then by fixing the skew, we get the similarity group. So that's just you can zoom in and out, and you can turn around, but you can't skew. And let's say you fix the focal length, so you can't zoom in and out anymore, then you get just a Euclidean group in 2D, so that's rotating and translating, and that's kind of what's been considered already in equivariant imaging. And if you fix the principal points, you can't translate as well, then you only can rotate, then you recover the SO2 rotation group. So this provides quite a nice way of, like a principled way of doing these kind of warping homography transformations. So these transformations are used quite a lot in industry, in practice, in data augmentation. So you have, if you go on the Torch Vision website, you have images, and then you can apply rotations, you can apply warps, you can pick 4 points and map them to any arbitrary quadrilateral. They're just, these are transformations that are the same as these, but we provided a group theoretic perspective on them.
So sorry, is that a bit like when you image like a QR code, it's automatically sort of...
Yeah, exactly. Yeah. So it's really, really commonly used in this image registration, or it's called demosaicing of the images. So yeah, so we've got this nice subgroup chain going from what's already been considered, so 2D rotations, 2D Euclidean transformations, all the way up to the 3D nonlinear and 2D linear and 3D transformations. So how is this relevant for satellite imaging? So as I've shown, this kind of setting is quite natural. Actually, satellites, when you maybe go on Google Maps, Google Street Satellite View, you see these kind of straight down looking images, but that's not the case in real satellite images. The real satellites, they're not always necessarily facing 90 degrees orthogonally down at the Earth. So you actually have quite a lot of perspective variability. And this is actually leveraged in a lot of modern satellites, because you can quickly turn from, let's say, a satellite's orbiting and it's facing this way, and an earthquake happens here or something, then it can quickly turn around. So real satellite images have this kind of perspective variability. Okay, so this is what these transformations look like. So starting with the most Euclidean ones on the left, and then so this is the SO3 3D rotation group. So that's just, you're staying in the same place and you're turning around for these two cases. And then these are the further groups that we discussed. So this is the most general one, so encompassing panning, tilting, affine, and scaling. And this is the affine subgroup. So I added in this slide because of the question yesterday. Can you just like use the biggest group for all your problems, and then you can just hope that it has the best results? So we actually showed that no, this is not the case. So in satellite data, you don't really want to assume, for example, shearing in the data. So you want a group that's big but doesn't have the shears in affine. So if you use the most general group, which is this perspective, the third line, we actually get worse results than if we only consider the subgroup, where you just do this. I mean, this is purely empirical. It'd be nice to have some kind of way of monitoring or measuring without ground truth, evaluating what is the best subgroup to use when you have a general description. Okay. Going quite quickly through this, so we know why invariance works and why it's useful and why it recovers information in null space, and we know how to enforce it using equivariant imaging. And then now we're just replacing simply the TG by a representation on action from these bigger groups that we discussed. And yeah, so going beyond what we've said here, is kind of lots more groups, and what is more? What else can we use? What other groups can we use? And then, yeah, how can they be applied to more different forward problems, different imaging? So if you're imaging different things, then you'll be able to come up with different beliefs of what the set should be inherited. So just general performance. So in both of these problems, so the dynamic MRI and satellite imaging that I've talked about, we're always approaching the Oracle supervised performance, and adding these larger groups, richer groups, supergroups, improves performance over the classic just 2D Euclidean proof. And then we're using real data. So in the cardiac MRI, we're using challenge data from 2 years ago now at really, really high undersampling rates and beating all other self-supervised methods, which we'll discuss later today. And in the satellite case, so really, really high downsampling. Interestingly, if you look through all this kind of pan-sharpening problem literature, every single other paper in the literature is just doing measurement consistency, so you can never recover anything from the null space. So, okay, let's put a slide in just whilst I'm here. So after the break, so after Marcelo's talk, there'll be a software introduction to deep images, me and Julian. So there's a few aims there. So how to do research in self-supervised learning. So how do you compare these different methods? Which methods are better than which are kind of these methods that we've discussed today, the past 2 days. And the workshop afternoon will be how to use these advances on your own data sets or inverse problems. Finally, as a conclusion, so we've considered 2 inverse problems where ground truth does not exist. And these are real problems that the fact that the ground truth does not exist is limiting their advances in the real world. So we need this unsupervised, self-supervised learning. We're constraining the problem using invariance, and by considering bigger groups, nonlinear groups, continuous groups, we're getting considerable performance gains. And as I alluded to, some kind of thought is what other beliefs could you use about data or imaging systems, different kind of cameras. So we've considered the satellite camera or the optical camera. There must be other cameras out there which obey. So for example, the ultrasound camera. And if an ultrasound rotates against the body, what is the transformation or the group of transformations induced by that?